system. I'm not sure I'm able to pronounce the names of the authors, so I'll let you pronounce yourself.
I'm Alexander. This talk is about MLton. It's about handling overflow in MLton. Hence the title. Yeah. For those who don't know, the MLton compiler is a standard ML compiler. It's open source, industrial strength, used by several companies, including hardcore processing, as we've heard earlier. It's a whole program compiler. It's optimizing, and it has been developed over the last 15 years. So, the handling overflow part. In an intermediate representation in MLton, arithmetic, integer arithmetic can take the form like you've seen above. So, two integer variables, some integer operation, pass the result to a label. If we encounter an overflow, move to another label. If this integer operation does not overflow, we can optimize this to a primitive integer addition that does not check for overflow. We have some bad news. MLton produces suboptimal code regarding overflow checks. Here's an example. When compiling the Hamlet SML benchmark, we find this snippet among the 110,000 lines of intermediate code. So I'll just rewrite this code a bit. Here's as a flow graph, a little bit simpler. The global constant in line, simpler. The variables are alpha renamed. So we have a Boolean comparison of an integer variable and a constant. The case transfer for this result is true. We add 1 to the variable x. If you overflow, what else? So on 32 bits, we know that x is less than 951. X plus 1 cannot overflow. So this could potentially do without the overflow check. So the question is, can we formulate a static analysis to improve the generated code? Here we have some good news. Yes, we can. So my talk is first about MLton in a bit more detail, then about detecting the dead code using interval analysis, the analysis itself, and the result. So MLton in detail, from source code to machine code, some intermediate steps and some transformations between them. At some point, we reach SSA, static single assignment. We've been to a monomorphized phase and a closure conversion phase. So we end up with a simply typed first order language. Static single assignment form, so each variable has one definition in the program text. And it is here at this level that MLton provides most of the optimization. So the standard way of analyzing integer variables is using a interval range analysis. I'm using a lattice like you see here. The mean and max are placeholders for the smallest and largest numbers representable by the bit width of the variable. And this, I make a lattice that relates variables to an element from this interval lattice. So I'll create a function that, given a variable x and a label, I need a interval for x. This initial version of the function simply ignores the label and gives me the entry in this I lattice. So it's a global product. I will find this later. So we have a lot of constraints. Here are a few examples. The simplest one at the top, it's a constant definition. So the element for x that is assigned the value v is simply assigned the constant interval, the element v. Another constraint is integer arithmetic, where we have some integer arithmetic and operation, pass that result to a label L. This, we perform the same integer operation on the abstract domain under abstract values of the two variables, and we flow that into the interval lattice that for the x variable that is the receiving parameter of this computation. There are more rules all regarding the flow of the propagation of abstract values throughout the program. Here's a non-tail call where we flow each value into the corresponding formal parameter. But this is not enough. My example from earlier, we have this Boolean comparison, and we have potentially some code in between this comparison and this case transfer. So we need something that can capture this information, this comparison, and something that can use this information when we need it later on. So we need some flow sensitivity. I write and lattice A. This means that for the variable x, if this variable is true, then the interval for y is the result of this expression. So create two functions that bounds intervals. I create this constraint. So when we need a Boolean comparison of two variables, if the result is true, then we know x1, the abstract value for x1 is less than the abstract value for x2, and the other way around for x2, and if it's false, then it's the opposite. So now this A captures the information from the Boolean comparison. Then we need to use this Boolean comparison when we transfer on this Boolean result. For that, we create a fact lattice F that's mapping from a block in the SSA code to a variable to an interval. So, case transfer on x. If x evaluated to true, then we have this. Then we know that the variable from the comparison y, we call this the interval we got from this y, and we propagate that into the fact lattice in the block L. That's the true branch for the variable y. And similarly, for if it's false, then we use the L prime. That's a wrong L here. It should be like this. And again for the other variable of the Boolean comparison. So we redefine our lookup function to search the SSA ancestor tree for facts about this variable. So we look, do we have a fact at this block where we want the value? If we do, return it. If we don't have value, and if we don't have any more ancestors in the SSA tree, then return the result from the global interval lattice. Or else look for the same value in the SSA ancestor for of the L. So we have implemented this as a proof of concept in MLton as an additional optimization pass. It takes approximately 1,500 lines of HTML. the pass is followed by the pass remove unused, so potentially dead overflow blocks are removed. That if no other path in the code points to this overflow block, then we can remove it. Here's the result from earlier, where we have the bottom line here is the overflow checking arithmetic, x plus 1, we have the Boolean comparison. It's been translated into the primitive add of x and 1, and the result is passed to the label. So this L triple prime is potentially not used anywhere else in code, and then it can be removed. So to test this, we used the MLton benchmark suite. There are benchmarks from 50 to 100. In the benchmark suite, in SSA form, there are 4,240 integer arithmetic, overflow checking integer arithmetic, and we transform 930 of those, so about 22%. So what does this give us? Size of the programs are reduced. Here are some of the, from the top, the best. Two are actually reduced 10% in size. Some are reduced less. Overall, we reduced the benchmark suite by 0.6%. On average, 0.85% of the binary size is reduced. And every benchmark has a reduced size, by the small one. So runtime, we are the best for a benchmark like matrix multiply with heavy integer arithmetic. We actually receive a 27% speed up in runtime. Again, three really good, all integer arithmetic heavy programs. There are some that have no effect on runtime, even though we have transformed some integer checking arithmetic. Of course, if the arithmetic is run once, then not much is gained in terms of runtime. And we have a few, two that actually have increased runtime. Rather strange, since we only remove instructions, so it must have something to do with cache missing, and memory alignment and so on. We haven't looked at that more, but yeah, we have reduced the number of operations, so the runtime should hopefully not increase. The average reduction in runtime is 1.8%. Here are some of the good ones. The matrix multiply reduced almost 2 seconds. So what about compile time? This should be noted that this is a proof of concept, so the data structures are basically just lists. So there are performance gains there. I'll come back to a few points more later. So the Hamlet is the largest benchmark. It's actually increased a bit, and compiling MLton itself with the optimization takes some time too. So yeah. But some of the small ones have a little reduced runtime. The average is 15%. So, what can we conclude from this? Well, by applying relatively straightforward static analysis, we can improve the code generated by MLton. We transform 22% of the overflow checking arithmetic. We reduce the size by 0 to 10%. we reduced the runtime of up to 27%. But as you saw with the compile time, there's room for improvement. In the choice of data structures, this was done as part of my master thesis. This is just one of two improvements I did, so the code is not optimized as such, but of course room for improvement in the analysis precision, and of course the compile time for the analysis. So here's the link to my master thesis. Thank you.